Hi guys, happy Monday. How's everybody feeling? Feeling like we have 1 week left, not even, like 3 days left? You guys know your final exam's on Thursday, right? Or what we're calling midterm 3. Okay, good, we're all in the same place. So, anybody getting anywhere on the chapter 25 homework? Anybody aware that we have chapter 25 homework? Anybody aware that there is homework for the class? What class are we in here? What is this?
Ice cream melting 25.
Yeah. All right. So my first thought was we were going to largely finish discussing chapter 25 today here in the video lecture. But my second thought is there's quite a few people that have labs right now, unable to view the video until later. So I was thinking we'd just make the homework for chapter 25 due tomorrow. So I'm going to do that right now, okay? So you got a little bit of a reprieve, and let's make that chapter 25 homework due tomorrow at 11:59, just like normal. And then why don't we take a look at a couple of the problems. So let's look at the first misconceptual problem and see what it's addressing. Okay, so this one says, if the distance from your eye's lens to the retina is shorter than for a normal eye, you will struggle to see objects that are far away, colorful, nearby, moving fast. Okay. So to answer this question, we need to know a little bit more about the eyeball and maybe even a little bit more about nearsightedness and farsightedness. So let's do that. We're going to draw the ideal eyeball. And remember what the eyeball looks like. You've got a cornea, there's a crystalline lens. On the back is your retina. You want to form images there. The ideal eyeball takes parallel rays and focuses those parallel rays to a single point on the back of your eyeball, on the retina. Okay? This is what the ideal eyeball does, the relaxed ideal eyeball. So when you look at a distant star, it looks like a point. The rays coming from that star are parallel. It should all focus down to a single point. But you, of course, rarely have an ideal eyeball. A few of you have ideal eyeballs, but a lot of you are nearsighted. Nearsighted is, of course, called myopic. And myopic means that you're not focusing the light quite at the right spot. So parallel rays coming in, again, will now focus too close. When they go in, they focus there, not on the retina where your photoreceptors are, okay? Farsighted, which is called hyperopic, means that parallel rays coming in into the eyeball now focus too far behind the eyeball. Okay? This is nearsightedness. This is farsightedness. So, when you think about if you're nearsighted or farsighted, how do you determine that? Well, the first thing you do is you take off your glasses and you hold up your book and you put it really close. And if you can read it when you're really close, then you're nearsighted. If you can't read it when it's really close, then you're farsighted. Okay, and this is obviously where they get the name. You can see things near or you can see things far. All right, so how do we deal with this in terms of this question right here? It says, if the distance from your eye's lens to the retina is shorter than for a normal eye, you will struggle to see objects that are blank. Here's our normal eye. Let's draw it again, but we're going to make the distance from the lens to the retina shorter. Okay, so now parallel rays that come in are still going to focus to the same spot as this first picture, except it's now behind the eyeball. Okay, so this is a shorter eyeball. Does this look like farsightedness or does this look like nearsightedness? It looks like farsightedness, right? It's the same picture that we drew for the farsighted case. So if you are farsighted, you can see things far, but you struggle to see things close. So let's click nearby and submit it, and it says we are indeed correct. Yeah.
Someone wants to go over the corrective lenses conceptual questions.
Okay. And who is that someone out there?
Hilda?
Hilda. Hi, Hilda. How you doing? Welcome. Everybody say hi to Hilda.
Hi, Hilda.
Somebody had their coffee today.
That's right.
I like it. Yes, let's do that. Let's go over eyeglasses first, and then we'll address that question.
This we good for Washington.
Yeah.
That's fabulous.
Yeah, I think we need like the really sort of rough shop rags, you know, that are almost feel a little coarse. Those seem to work pretty well. Okay, so let's say you are nearsighted, okay? If you are nearsighted, then you can see things that are near, which means if this is my eyeball, I can see things that are near. And if this object is near, then the rays coming from the object are diverging. And the power of my lens means I can focus those back to a point on the back of my retina with no problem, okay? This is nearsighted. I can see things close. The rays from that are diverging. But you want to be able to see things at distance, okay? And so at distance, the rays that are coming in are very close to parallel. And you can't focus those to the right spot, either because your eyeball is a different size than normal or the focusing power of your cornea is different, okay? So all we have to do is take parallel rays from this object and make them diverge. And we know how to do that, right? We use a diverging lens. And when those parallel rays come into this diverging lens, they're going to diverge. And if they diverge the same amount as we had up there, everything's going to come back together. At the retina, it'll be in focus. So for nearsighted, you add a diverging or negative lens. Okay, that's how you fix nearsightedness. But what about farsighted? If you are farsighted, then you're looking at parallel rays coming in from a distant object. Here is your eyeball. And if you're farsighted, then they don't quite get to a focus right where they should be. Okay? So we need to get that focus in a little closer. And the way we get it in closer is we add a converging lens. And remember, converging is positive. Okay? And so parallel rays that come in, we want them to focus on the retina, and so we add a positive lens right there. And that starts to get these rays to bend in a little bit, and now they can come to a focus right on the retina. So, you automatically know if you are nearsighted or farsighted just by looking at your lenses. Okay, so here, these are my reading glasses. Okay, when you get old like me, you get reading glasses. And these have a positive value. They're converging, which means I am farsighted. I can see things at far just fine. But when I try to read things close without glasses, then it's hard to read. Okay? And so I need a converging lens. Now, how do you know this is converging versus diverging? Well, first off, if you look through them, at some point, the outside world should get very big as I move this away from my eyeballs. And if you look at that camera, right, if I'm looking at the camera, my eyeballs should look a little big to you. Do the eyeballs look a little big to you? And especially if I pull them out a little bit, let's try this. I'm trying to do it without getting shadow all over the place. Okay. This eye should look big to you guys on the computer monitor. Okay, that's how you know it's a positive lens. If it's a negative lens, the outside world will always look smaller. Okay? And when you look at a friend and you do this, your eyeball will always look smaller if it's a negative lens. Okay? So this is a converging lens. The other would be a diverging lens. Now there's other things that you can figure out here. One is there is a little bit of astigmatism, which means it's not a spherical lens. There's actually a little bit of cylindrical shape to it. And the way you can tell that with somebody's glasses is if you look through it and you rotate it, and the image goes from squished this way to squished this way, that's astigmatism. And if you look at my glasses, my left eye is more astigmatic than my right eye. So when I rotate this, the image in the right one doesn't get as distorted as the one in the left one. And when I look out at you guys, you become very distorted in that left lens. The other thing to know about nearsighted versus farsighted is a positive lens means you can focus light down to a point. Okay? So if you are out in the sunshine and you're trying to focus light to a point on a piece of paper because you're trying to start a fire because you're on a desert island, you had better hope that the person's glasses you're using, they're farsighted, positive lens, so you can focus that sunlight to a point. If they're nearsighted, it's never going to help you start a fire. Sunlight that comes through there diverges everywhere. Okay? So one more thing before we attack the conceptual question, and that's this idea of lens power. So when you go get your prescription at the eye doctor, it will say on your prescription for your contacts or your glasses, it's basically the same idea. You're going to get a prescription that says, oh, plus 2.5 or plus 3.0, or plus 3.5, or negative. What does that number mean? What is the lens power? Power, or more specifically, refractive power, is 1 over f. Okay? It's just 1 over the focal length of the lens. So this is measured in something called diopters. And diopters is, of course, just 1 over meters. All right? So if you have a +1 lens, if your power equals +1, then that means the focal length is 1 over that. It's 1 meter. But if you have a power of 2, focal length is 1 over that, which is a half a meter. Okay, so my glasses here, the left eye is a +3 and the right eye is a +2.5. And that means that the focal length here is about 1/3 of a meter on this side. Okay, 30 centimeters. If you have negative numbers for your prescription, then you have diverging lenses. So if your power equals -2, then your focal length is -0.5 meters. Okay? And so when you look at your prescription, you can tell right away, do I have eyes that need a big converging lens, a lot of power, or something that's a little more relaxed, a little more loose? Okay, so let's think about power in terms of your eyeball. Okay, what we said was the power is going to be 1 over the focal length. And now we're worried about the focal length of your eye. And we talked about the focal length of your eye last time. It has to be basically the size of your eye, which is about 25 millimeters. Okay? And so this is 1 over 25 times 10 to the minus 3 meters, which is 40 diopters. Okay, that cornea is very curved. It's a very powerful lens. And these are sort of typical numbers for your glasses, right? So when I think about the glasses that I put on to read and I'm going to add a power of 2.5, that's going on top of 40 diopters already. So it's a small fractional change. And the way you can tell this is if I just look at the glasses edge on, they're not very curved. Okay? They're a little bit curved, but not very. And if I look at my eyeball edge on, it is really very curved, right? It looks like a marble. The more it's curved, the shorter the focal length, the bigger the lens power. Okay, so let's attack the conceptual questions. And let's take a look at number 2506. I think it might be more pen dependent than cleaning dependent. Okay, so 2506 says the following. It says, how do eyeglasses help a nearsighted person see more clearly? All right, I don't think we need to go over that one since you guys just went over that one. I think you can probably figure out which one is the right answer. Let's take a look at the next misconceptual question. It says, while you are photographing a dog, it begins to move away. What must you do to keep it in focus? Okay, so let's go back to the camera. The camera is just like an eyeball, right? It's the same idea. So let's draw a camera. Here's the lens of the camera. Here is the film plane, or the CCD plane. Okay, this is where your retina would be in your eyeball. And it says we got a dog that we are photographing and it's in focus, but then it's going to start to move away. All right, so we draw a dog. Here's our dog. Happy dog. Okay, and we're taking a picture of this dog and he's in focus. All right, so if I think about the rays coming off the dog when that dog is close, how do I figure out where those rays are going to end up? Well, let's draw some focal points. Let's say there is a focal point here and a focal point there. And now this is just like our good old object. So we're going to erase the dog and just draw an arrow like we usually have. Okay. And now let's see if we can figure out where it's all in focus. Parallel rays go through the focus. Rays through the focus, go parallel. Everything is in focus right here at the film plane. Good. But now, this thing is going to move further away, okay? And if it moves further away, we're going to have to do something to keep it in focus. So let's draw a picture again. It looks like that. But now, parallel rays go through the focus, rays through the focus go parallel. And look what happens. The image should be in focus right there. And yet, our film plane is fixed. Okay, we can't move where the film is, but we can move where the lens is. So if I want to move that image to the film plane, which way should I move this lens? Should I move it closer to the film or further away from the film? I have to move it closer to the film. If I move the lens to the right, the image is going to move to the right, everything is going to move to the right. So I want to move the lens closer. Okay. And let's see if that is the right answer. It says move the lens closer to the sensor or the film. Sensor's CCD array if it's like your digital SLR. And it does say that that is the right answer. Okay, so when things get further away, you want to move the lens closer to the film. And in fact, when they get out at infinity, the focal point should be at the film plane. Okay. Hilda, if you're still watching, did that seem okay? All right, let's ask you a question. Why can't you focus underwater? Okay, let's say you go swimming, right, underwater, and you're not wearing a mask, you're just floating around down here. Here's your big old eyeballs. You're having a good time, and you're trying to see this fish, but it looks all blurry. Okay, the fish looks blurry. You have a hard time focusing underwater. Why is that? To understand this, we need to think about what's happening to the rays of light that are coming from the fish to our eyeballs. Okay? And let's draw a couple pictures here. Here's your eyeball. And when parallel rays come in, they are focused to a point at the back of the retina, okay, at the back of your eyeball, at the retina. But let's draw it in a little more detail to see what happens in this bending at the cornea. This is the cornea of your eyeball. And when this parallel ray comes in, it's going to hit this first interface. This is air out here. This is your cornea. There's the rest of your eyeball. And so there's going to be bending at that first surface. The light is going to bend at the cornea. And it's that bending at the cornea that's going to allow it to focus on the back of your eyeball. But why does it bend there? Right? It bends because Snell's law says n air sine theta air equals n cornea sine theta cornea. And there is a different index of refraction between the air and the cornea, and that means that theta has to change. Okay? It's going to bend towards the normal. Since the cornea is curved, those parallel rays will bend inward towards their relative normals. But what happens when you're underwater? When you're underwater, here come the light rays in. Here's our cornea. There's our eyeball. And now, we're not in air anymore. We are in water. And so Snell's law says that n of water, sine theta of water, equals n of the cornea, sine theta of the cornea. And so it's going to bend if those are different, and it's not going to bend if they are the same. And what happens is those are nearly the same. N water is nearly the same as n of the cornea, and therefore theta in the water is nearly the same as theta in the cornea. Things don't focus, and so you can't see underwater. You can't focus very well underwater. Now, anybody know why this would be? Why would your cornea have nearly the same index of refraction as water? Any ideas? Because you guys are made up of water, okay? You are mostly water. And so the cornea has nearly the same index as water because a lot of it's made of water, all right? Sort of this gelatinous stuff, but it's the same idea, okay? So how do you fix this problem? When you're swimming underwater and you do want to see those fish, how do you fix the problem? You get an air-water interface again by putting on a mask. And by putting on that mask, you put a little air in front of your eyeballs, and when the light rays come through now and they go to the air cornea interface, they can bend and come to a focus. All right? This is the whole reason for the mask, is just to provide a little air next to your eyeballs. In fact, you don't need a mask. If there was another way to provide air right there, you can do it. And you've seen this before, right? If you take a big bucket and put it over your head and you go underwater, and now there's an air gap between the water level and your eyeballs, then you can see just fine again. All right? Yeah?
Hilda was talking about number 5.
She was talking about the one we skipped, huh?
No, number 5.
Number 5. That was the...
Refractive lenses, conceptual questions.
Okay, hold on. Let me figure out which one she's talking about. Okay, gotcha. There it is. All right, let's take a look at that one. Samuel, can you switch the monitors and pop this one up by chance? Okay, so this was number 5 on the homework. It's entitled Corrective Lenses Conceptual Questions. And it says, the near point, the smallest distance at which an object can be seen clearly, and the far point, the largest distance at which object can be seen clearly, are measured for 6 different people. Which, if any of these people, are nearsighted, which would require bifocals, which would require converging lenses, and so forth. All right, good question. So let's just take a few examples and let's see what we can determine. Okay, what we said before was the closest point you can focus, that's the near point. Okay, and what do we mean by that? Well, here's our eyeball. Put the object here, and if it's there, then it comes to a focus on the back of the retina. That distance is your near point. Okay? The farthest distance that you can measure is, of course, called your far point. And for normal eyes, that is infinity. Okay? But if your eyes are not normal, then it's some other distance. Okay, and it's always relative to the lens of your eye. So this would be the far point. Okay, and that would come into focus on the back of your eyeball as well. Now, you can change the near point by adjusting your crystalline lens in your eyeball. So when you squeeze on that lens, it gets a little more bulbous, increases its focusing power, and that allows you to see things close. Seeing things far away is when your eye is relaxed. Okay, so when you relax the muscles, the ciliary muscles that are crushing that crystalline lens, when those are relaxed, then that's your far point. Okay, so let's take a look at the first person. The first person was Avishka, is her name, and they had a near point of 40 centimeters and a far point of infinity. Okay. So, when you consider people that are nearsighted, they are not able to see out to infinity, right? If they can see out to infinity, then they are farsighted. Likewise, if they can't see anything close, then they are farsighted, not nearsighted, where the close point is about 25 centimeters. Okay, so this person right here is farsighted. Okay, the next person, Bernice, has D near of 30 centimeters and a D far of 300 centimeters. Okay, so that person is interesting because they can see something relatively close, not quite 25 centimeters, but they certainly can't see far away. And I would suspect that they would satisfy the question for part B, which is they might need bifocals to correct their vision. Okay. Since they can't see far away, I would also put them in the category of nearsighted, meaning when they drive, they need negative lenses so they can see out to infinity. Okay? If you can't see to infinity, then you need negative lenses, you are nearsighted. If you can see to infinity, you are certainly farsighted. All right, and then there's a few more questions that continue, but basically the idea is this. If D far is less than infinity, you are nearsighted. If D near is bigger than 25 centimeters, then you are going to need reading glasses or positive lenses. Positive is another word for converging lenses. Okay? And that 25 centimeters was solely picked basically on the length of your arm, where is a comfortable reading distance, and so they picked 25 centimeters for that. All right, so we're not going to belabor this one just because there's a lot of different options that you can click on, but I think that'll get you started on that one, hopefully. All right, let's talk about colors for a second. So when we think about color, we think about maybe drawing of different colors, right? So here's pink, here is green, here is blue, okay, and let's label this. This is blue. This is green. We're going to call the top one red. It's really looking kind of pink to me, but let's just call it red for now. This is red. So when you think about different colors, you think about how am I observing those different colors with my eyeball, of course. How do I know that that's red, that that's green, that that's blue? Because you grew up on this planet, and your teachers and your parents told you all along, look at that, that's blue. Look at that, that's green. That's red, okay? People gave you names to these different colors, but when you get into shades that are in between the colors, and you start mixing colors, now you get into all these other names, right? And they're very subjective. So color is very subjective. It is your observation of the world. Okay? There is no definitive wavelength that is red. There's no definitive wavelength that's green or blue. There are ranges of color, and the visible spectrum goes from about 400 nanometers up to about 700 nanometers. And down at the low end, we've got blues. And somewhere in the middle, we've got greens. And somewhere up above, we've got reds. Okay. And when you think about all the colors in the rainbow, one of the things that they taught you was Roy G. Biv. Right? What does that mean? Red, orange, yellow, green, blue, indigo, and violet. Okay, red is long wavelength. And violet is short wavelength. Okay, so reds are up here in the 600 to 700 range. Blues are down there in the 400 to 500 range. Okay, and then in between, you have all these different colors. So when you think about putting colors together, we picked red, green, and blue for a particular reason. And the reason that we picked those is because your computer monitor is made up of red, green, and blue dots. RGB. That's what RGB means, red, green, and blue. Okay, so if you look at any computer monitor or your smartphone and you really zoom in on those dots, you'll see bars of red, bars of green, and bars of blue. And it's only when you step back and look at them all on top of each other that you can see the combination of those. So there's something called the color wheel that we can talk about. And the idea with the color wheel is the following. If I have RGB, like in your computer monitor, and I add them all up, red plus green plus blue, I get white. Okay. Turn on all the pixels on your computer monitor, you get a white pixel because you're adding up the red, green, and blue. But these are not necessarily the only primary colors you can use. You can also use cyan, magenta, and yellow. And when I do that, I also get white. Now, for technical reasons, most computer monitors are RGB. Most printers are CMY or CMYK. The K means color temperature, which is how much black is in your image. But let's see how these things overlap. So if I think about a region here of red, and I think about a region here of green, and a region here of blue, then in this overlap region, between red and green, I get yellow. And between green and blue, I get cyan. And between blue and red, I get magenta. And if I add all those things together, then I get white. And so these are primary colors. If somebody says, what are the primary colors? A valid answer is red, green, and blue. But another answer is cyan, magenta, and yellow. And in fact, if you rotate around here, you can pick all sorts of different primary colors and still get them to add up to white. Now, if we think about red, green, and blue in terms of that spectrum, they don't really look like we just drew it. They're not blocks. They're actually sort of distributed regions. Okay, and so this first one is blue, and this one is green, and this one is red, and this is maybe 380 nanometers down here, and this is 700 up there. But there's some overlap in those regions, okay? There's some tails on either end, and so when you start mixing, you can take advantage of those overlaps. Now, there's two types of colors that you have to worry about. There's additive, and this is when you overlap bright pixels, like in your computer monitor, okay? And that's RGB. But subtractive is when you overlap inks. So if I take red paint and green paint and blue paint and I put them all on top of each other, I don't get white, I get black, okay? Those are subtractive colors. And because the paint is red, that means it absorbs everything except red, okay? My shirt is red because it's absorbing the other colors except red, and those colors are bouncing off to you. But if I put blue paint on my shirt and green paint on my shirt, now it's absorbing not only the stuff blue and green from the original colors, it's absorbing the greens and the blues and the reds and all the other colors as well. It'll turn black, and that's subtractive. So these are inks. Additive colors are when you do bright beams, like the pixels on your computer monitor. Okay. Now it's kind of weird to think about, because if you look at your computer monitor and it looks white to you, when you take a spectrum of it, if you take a monochromator and look at the spectrum, you will see this. Okay? You won't see a full color distribution. You'll see blues and greens and reds. And yet when I take sunlight and I take a spectrum of sunlight, it does fill in all those gaps. Okay? Has all the colors in the rainbow. Even though those two might look exactly the same to you, they can have very different spectral signatures. And this is something that's weird about your eyeball. In your eyeball, you have sensors that are red sensitive, green sensitive, blue sensitive, and somehow your brain interprets all that by putting them together and making white. Okay, let me tell you a quick little story, and then we'll take a break. So let me show you a device. Let me see if you can see this. Can we turn down these lights a little bit? Why don't we turn at least one of them off?
Turn the bottom.
That's good. That's fine. Okay. Can you guys still see me on camera, Samuel, or not so much?
You're good.
Okay. So this is, let me turn it on here for a second. I'm going to ask you a question about this. And you'll see why I wanted the lights off. Okay, can you guys see that bright white ball?
Yes.
Yeah? Let me come on the other side of the glass. Can you see me on camera, Samuel?
Nope.
Okay, perfect. But you can see the ball, right?
Yes.
All right. So when I look at this white ball, it looks like white to me. It's maybe slightly off white, but it looks white. Is it white? She's shaking her head no. Why are you saying no?
I don't know, when I'm looking at it, it looks like it's like a combination of like 3 different colors.
Ah, there's something weird going on there, right? And are you seeing that when you move your eyes around? Okay, so now I want you guys to try the following. I want you to look from the left side of the screen to the right side of the screen very quickly. Okay? What color did it look to you when you did that?
Green, red.
Okay. There's an easier way to do that, which is this. Right? Let's spin it around. And if I spin it around, you see that what was white is in fact made up of 3 colors. And I can change the refresh rate here, the speed of this thing. Let's try to get it going fast. There we go. Okay, so now I would say that looks pretty white, right? There it is in front of my face. But yet when I spin it, it's clearly red, green, and blue. Okay, so these are like the pixels in your computer monitor. If I turn them all on at the same time, it looks white to you. But for some reason, when I do this, it doesn't look white anymore. So anybody know how this works? Are there really red, green, and blue on at all the same time? No, they're not. It's flashing between red and green and blue very quickly. And in fact, it's flashing so fast that when you look at it straight on, you can't tell the difference between the flashing and the average of them all, which is going to look white to you. And that's because it's hitting the exact same retina, the part of your retina, over and over again. And your eyeballs are kind of slow. So anything faster than about 10 hertz looks continuous. If I flash this slow, now you can see it flashing. Okay, you can clearly see it flashing between red, green, and blue. But as I turn up the frequency, you get to a point right there where all of a sudden it starts to look continuous again. Okay. And that's because your rods and cones are a little slow. But if I rotate it, now you're hitting different rods and cones. And so different parts of your eyeball are being activated, red, green, or blue. And that's how you can distinguish it. So this is kind of a nice example of mapping something in time to something in space. And the other fun thing is you can go through all different color patterns. So there, if you're feeling particularly patriotic, you can go red, white, and blue. And then there's our rainbow. And there's a little Rasta maybe. And then we go to Miami Vice colors, right? And this is one of my favorites right here, okay? The fast strobe pattern, where they just sort of hover in midair. So I wanted to show this to you because, one, I think it's a nice demonstration of color mixing, but two, this is a toy that I invented with a buddy in grad school. It's called Strobe Effects, and we licensed it to a company called Spin Master, and they made and sold these all over the United States. So, kind of a fun little story. All right, let's take a 5-minute break, and I will see you guys back here in a few. Hi guys, welcome back. Let's take a look at one of your homework problems. This is one that people have chimed in about from home, and it's 2526. And in this one they say a small insect is placed 6.4 centimeters from a 7 centimeter focal length lens. Calculate the position of the image. Follow the sign conventions. Okay, so let's see if we can draw the picture, and let's put down the givens. They tell us that DO is 6.45 centimeters. They tell us F is 7 centimeters, and we need to find DI. Okay, let's draw a picture of this thing. Here's our lens. They told us that it is a 7 centimeter lens, and that is a positive number, so it's a converging lens. So let's put the focus right there, F, on either side. Now, they tell us that the insect is placed 6.45 centimeters from the lens. And so the insect is in fact closer to the lens than that focal spot F. So we have to follow our rules again for determining where the image is, and then we'll use the thin lens equation to do the calculation. So parallel rays go through the focus. That's rule number 1. Rays through the center don't bend. That was rule number 3. Do those two rays ever meet over here? Dave says no. Anybody else? They don't, right? They are diverging still. So they're never going to meet over here. So there cannot be an image located on this side. All right, so how do we determine the image? Well, you trace this one back, you trace this one back, and where they meet, that's where the image is located. Okay. What does this mean? It means if I stood here and looked at this thing, where would I perceive the image to be? I would perceive it to be right there. Now, let's make sure that this jives with the thin lens equation. So if we go to the thin lens equation, we have the following. 1 over DO plus 1 over DI equals 1 over F. And we're looking for di, so we can solve this for di. We get 1 over di equals 1 over f minus 1 over do. And so we get di is equal to 1 over f minus 1 over do. And now we can put in some numbers. So let's try that. If you have a calculator, pull out your calculator and tell me what you get. We've got 1 over 7. We'll just keep everything in centimeters, that's fine. Minus 1 over 6.45. And if you try that in your calculator, tell me what you get. I'll see if I can verify it here. Anybody get an answer for that one? Okay, that's what I got. 82.1? Yeah. Okay. Negative 82.1 centimeters. So what does it mean to be negative? Remember, if the image is over here, then it is positive. But if the image is over here, then it's negative. So that's what the negative means. Negative means it should be over there. Now, it also says negative 82.1. Doesn't really look like it from our picture, but we got a little creative with these lines because I knew we were going to run out of learning class here. So we could believe that negative 82.1 would do it. So let's try that. Let's plug in negative 82.1 and see if we get the right answer. It says correct. All right, good. Second part says calculate the angular magnification. And remember what magnification is. M is equal to the height of the image divided by the height of the object. This is the height of the object. This is the height of the image. And you can do a little trig here to show that this is the same as the image distance over the object distance, except there's a negative sign right there. Okay? And now we have all those numbers. Negative di means positive 82.1 centimeters. Do, they told us, 6.45. So if I divide 82.1 by 6.45, let's see what we get. Let's add one more parentheses here so we know we're doing it right. Okay, I got 12.72. Yeah, it's a negative here because I forgot to add the extra negative sign. So let's just verify. Yeah. Okay, 12.72 for our magnification. We know it's got to be bigger, right? Clearly it looks bigger. 12 sounds like a reasonable number. So let's try that. Okay. Didn't like my answer very much. Did anybody get a different answer when they plugged that into their calculator? You got the same thing? Okay. So let's see what they want. Okay, so we'll have to look at this one because they're telling me it's 3.9, and that does not sound right to me. So we'll have to take a look at that one. Who sent in that question, did they say?
Carmen?
Who did? Carmen? Okay, so we'll take a look at that one, Carmen, and see if there's a typo in mastering. Sometimes there's a typo. This is what I get when I do the problem. All right, let's talk about magnifying glasses. Okay, so a magnifying glass is something you have probably used at some point in your life. And a magnifying glass is designed such that you can see small things, right? You can't read the font on the page, you use a magnifying glass and now you can see it. So let's think about the bare eyeball for a second. No magnifying glass. And let's take a look at an object. Okay, here's my eyeball, there's the object. I can follow the various lens rules, but really the only one that I need is ray 3. And ray 3, according to our lens rules, is go through the center of the lens and it doesn't bend. So that one went through the center of the lens, it didn't bend. The image is therefore going to be that big, okay? But if I move the object closer, what's going to happen? Okay, here's my picture again. And now when I move the object, and we'll try to draw it basically the same size, if I think about ray 3, that image got bigger. And it got bigger because ray 3 was steeper, right? Ray 3 came in at a steeper angle. And you know this, of course, right? If I look at text this far away, it's pretty small. As I bring it in, it gets bigger and bigger and bigger. But at some point, I can't focus on it anymore, right? I'm going to get to a point here where I can't focus. And so let's put an extra lens right against our eyeball. So here's the eyeball. Here's the object, same position. And now let's put an extra lens right there. That's our magnifying glass. And if it's right up against our eyeball, then the ray 3 follows the same trajectory and it's the exact same size. The image is the same size in both of these pictures. Okay, here's my big lens. Okay, this is a particularly powerful lens. And now if I want to look at something, the way I do it is I put the lens right up against my eyeball, and then I can bring the text in and I can see this far away. Okay, that's very close. Can you guys see my eyeball? So, what's the purpose, right? What I just said was if I bring the object in here, it's going to be big. But if I put a lens here and then bring the object in, it's going to be the exact same size. So what is the purpose of this magnifying glass? Well, it's this. If I put it here, I have a nice big image of my text. If I take it away, I have the same size image of the text, but I can't read it because I can't focus on it that close. And so this is the whole point of the magnifying glass when used in this manner, right up against your eyeball. It just does the following. It simply allows you to focus much closer. That's it, and it's really obvious with this sort of demonstration. Okay, so if you want to try this after class, you can come up and look at it. But if I look at a particular piece of text and I go like this, it's nice and clear, it's big, and if I take the lens away, it's still big, it's the same size, except it's way out of focus. I just can't focus that closely. Okay, so let's put in some math here to this problem. So let's draw the picture again. There's our eyeball. We have an object out here. It has a height, HO. It is at a distance, DO, from the eyeball. DI is the distance to the back of the retina. And we just said that the angular magnification will lead to an HI right there. And we've got what we can call an angular size to this thing if we define this angle theta. Now, since this ray didn't bend, angle theta there is the exact same as angle theta there. And so we can write the following. Tangent of theta is HO over DO, or HI over DI, right? Tangent is this side of the triangle over this side of the triangle, HO over DO, which is the same as HI over DI. And now for the small angle approximation, we have the following. Tangent theta is basically the same as sine theta, and we're just going to call that theta. And remember, theta is in units of radians. Okay, and so we can write down the angular size. Theta is just going to be HO over DO. Okay, so this might have been where we went wrong before when we were calculating part B of that other problem. And it's because the object was so close to the focal point that the image got huge, and we might not have been satisfying the small angle approximation anymore. Okay, so when you revisit that problem, look at not doing this, but just doing this and trying to solve for theta that way. I think that might be where we went wrong. Okay, so this is the picture with the bare eyeball, but now we're going to add the extra lens. Okay, so let's redraw the picture and let's put in that extra lens. So we're going to add a magnifying glass right in front. And now the object can be a lot closer. The object height is still the same, of course, but DO got smaller. DI is the same, and let's call this the image height prime now, some new image. And HI prime is clearly bigger. And it's just bigger because the object is now closer. Okay, so what's the magnification? Well, if we call this theta prime now, then we have the following. The magnification, M, is theta prime over theta. What is our new angle compared to our old angle? And this you can show it is the following. It is approximately N divided by DO, where this N is the following. It's the closest distance without the lens divided by DO, which is the closest distance with the lens. The magnifying glass, the extra lens. Okay, so you do a little bit of math here. And we're not going to do it here, but we will signify it by this squiggly line. And what you can find is the magnification is going to be 1 over f minus 1 over di, all of that times n. Okay, let's talk about devices that really magnify, like microscopes. Okay, so you're all familiar with this idea of a microscope. You've, I'm sure, looked through a microscope at some point in your life, right? You put the bug on the table and you take your microscope and you zoom in and you can see the bug in great detail. So a microscope, in fact, has 2 lenses in it. Okay, it is a 2-lens system. And there is an objective and there is an eyepiece. Okay, and we're drawing it vertically because these things are usually mounted vertically on the table. And you put your sample right here. And then you, of course, look down through this eyepiece. Now, there is some sort of housing between this stuff, and that housing has a particular length associated with it. And that length is given by L. And then there is a focal length for the objective and a focal length for the eyepiece. And we would like to know what is the magnification of the whole system. Okay, and this is a little bit tough, the derivation, so we're going to jump to the answer. And if you really want to see the full derivation, you can come visit me in my office. But the magnification M of a microscope is the following. Negative L minus FE times N divided by FO FE. What are these different things? L is that length that we just talked about. It's the length of this tube, okay? And that's usually about 16 centimeters for a microscope. It's purely governed by how high is the table. When you're sitting and looking down, what's a comfortable point for you to view it? That determines the length L of that tube. FE is the eyepiece focal length. Okay, so that eyepiece up there, you can actually pull it out on the microscope and look through it. It's a very short focal length eyepiece. FO is the focal length of the objective. Okay, so that's the thing on the bottom, and usually you can rotate different ones, and they'll say like 16x, 20x, 100x, right? Those are also very short focal length lenses, and they sit very close to the sample. N is the near point of your eye, and that is usually written as 25 centimeters. Okay. Length of the tube is usually about 16 centimeters. So you want good magnification in your microscope. And if you look at this equation right here, that means you want this number down here to be small. And so a microscope, in fact, has a short focal length FO, and it has a short focal length FE. Both of those lenses have very short focal lengths. And like I said, you can take them out and you can look at them individually. Okay. When you go to a jeweler and they pull out their loop to check out your ring and see if it's real or not, okay, they are using one of these things. Either one. It's just a short focal length lens. And that allows them to look at it very closely, just like we did with the magnifying glass. Okay? But put them together in the right orientation, and now you get dramatic increase in the magnification because those are multiplying each other down here. So if both those things are small, M can be very big. And you've looked through microscopes that are 100x, 200x, 500x. Okay, you can get incredible amounts of magnification. Yeah?
Jamie wanted to clarify, so for magnification, N equals 25 centimeters.
Mm-hmm.
The lens is your eye.
N is the average near point of a human, which is 25 centimeters. Yes. Okay, something very different happens in a telescope. So to understand the telescope, we first need to go back to the single lens discussion. Okay? And let's say that we do the following. Let's say that we have a single lens, and now let's put an object right there. I'm going to change colors because that pink is really squeaky today. You notice that? All right, where's the focal length of this lens? Let's put the focal length right there. If the object is there, where is the image? We just did this one a second ago, but let's redo it. Parallel rays go through the focus. Rays through the center, don't bend. The image clearly can't be located over here, right? These rays never meet. But if I trace these rays back, we did this one a second ago, it looks like the image is right there. This is where our image is. But let's add a second lens now. We know that a telescope has 2 lenses in it. And keeping this in mind for a second, let's go back to the 2-lens system. So a telescope has an objective and an eyepiece. And we want to see a distant object. The distant object means that the light rays coming in from it are nearly parallel, and so it's going to form an image right in here. And now you're going to image that image with the eyepiece to send it to your eyeball. So there is another derivation that goes along with this problem that is a little bit tricky, but the idea is when you are looking at this image, it can in fact look a lot bigger than it would look if you're looking straight at the object. And there is a magnification for the telescope, which is the following. M is again given by theta prime over theta. What is the angular magnification with the telescope versus without the telescope? And in the telescope case, it becomes this, negative FO over FE. The negative sign just means it's upside down. Don't worry about that. This is still the objective focal length. FE is the eyepiece focal length. So in your telescope, if you want a large magnification, then you want the number up top to be big. You want a long focal length objective, and you want the number in the bottom to be short. And if you think about a telescope, and you've all seen telescopes, okay, that first lens that it hits is very far away from your eyeball, and it's not very curved, okay? It's fairly flat. That gives you a long focal length objective. But the one at the other end of the telescope, the one right next to your eyeball, that has a very short focal length lens, okay? It looks just like the eyepiece of a microscope. So a telescope, you want long objective, short eyepiece. Microscope, you want short objective and short eyepiece. So they're a little bit different design, but it's basically the same idea. You're trying to take small objects and make them look bigger. The only difference is, are those objects far away? Then you need a telescope. If they're close, then you need a microscope. Okay. Any questions about that stuff so far? Everybody feeling okay?